Okay, everybody, this video would be the final video in solving problems in the elimination reaction. As I already said before, it's very important that before embarking on solving the problems, I encourage all of you to just review the lecture part of my videos. The elimination reaction is summarized in 3 lectures. Lecture 22, 23, and 24. And then I have about 3 videos already on problems in elimination reaction prior to this. This video would be the last in the elimination reactions. I'm sure that this portion or the problem solving sections of each chapter would give you a better understanding of organic chemistry, and it would give you a better understanding and also problem solving ability of any kind of problems in organic chemistry. I really thank all the followers from different parts of the world, United States of course, in Africa, in Zambia, Ethiopia, and also in Iraq, Israel, or in Belgium, and also in Italy. So I'm really thankful for all the subscribers. Anyone who you think that is useful, this video would be, please share it among your fellow students and colleagues. Thank you so much. So I'm gonna solve this problem, and this problem is what is the product and give the correct stereoisomer. So here the main important point of this problem is to give the right stereoisomer, either E or Z isomer in the alkene. So the initial starting materials are stereospecific enantiomers, clean enantiomers. Remember in chapter 5 we learned about stereochemistry. So if I just start by labeling what stereochemistry they have, that would be an essential addition to solving this problem. So this is a formation of an alkene by dehydrohalogenating from alpha, the alpha halide, and also the beta hydrogen. So if you just look at here, there are more than 1 beta carbon in this compounds, but we are only dealing with the internal beta carbon, not the alpha carbon here, the beta carbon outside, because the reason is we want to form a stereoisomer. So we are just dealing with only the internal alkene formation. You can still form alkene from here, but for giving E and Z, the internal alkene, which is a result of losing a hydrogen from here, and this one, a halide, would give you the stereoisomer. So this is a specific enantiomer of RR. This is an RR, meaning that this is an R carbon, this is also an R. This one would be now R, this is S. So this would be an S, this is an R. This is S. Oh, this is SS. Sorry. This should be an SS. This is SR. This is just, I already solved this prior to coming to you. So you should also practice back. This is in chapter 5, how to assign stereochemistry. You don't have to assign stereochemistry for the starting material, but it's good to know that what stereochemistry it has. So whenever you are given a stereochemically pure compound like that, and you are asked to solve or to come up with the E or Z alkene after dehydrohalogenation, you need to remember how to draw a Newman projection. So this problem is more than just giving a product. So remember how we drew Newman projection for a compound. Okay, another concept. The reason why we write in the Newman projection is that the hydrogen and the halide, the hydrogen that would be abstracted and the halide, they should be anti-periplanar. That means in the E2 reaction, this is a requirement. The E2 mechanism of elimination needs the hydrogen that would be abstracted and the halide that leaves, they should be at 180 degrees and on the same plane. So I will draw each one of them as arranged by the free rotation, which is possible for the free rotation. So the Newman projection for the first one, I will draw it in a very small scale. That is a propyl chain. That is the back carbon. I'm looking from this front carbon. So the front carbon would have chlorine here, CH3 there, and down there would be the CH3, which is this one. So this is the circle one, is that CH3. And this CH3 is the one, if I just color this with a black one, that would give you this CH3 is this. So it's very important for you to be very efficient in drawing the so the CH3 now would be actually that's actually H. So this should be H. H, and the CH3 would be this CH3 on the back. So that is the one with the black. And we have another hydrogen, which is for this one. It would be this. So it is equivalent to that. So the Newman projection of this compound is that Newman projection. So if you just look at this, you don't have to rotate any of this, because this hydrogen, the one which is in a blue box, and the Cl, which would leave as a hydrochloric acid, are anti-periplanar. Already they are on the same plane, and also they are 180 degrees. So no rotation. Without no rotation, you could find things that are already lined up. So the dehydrohalogenation of this would give you these two CH3s on the same face, and this propyl and this hydrogen on the same face. So if you just do the elimination with a base, this is an E2 reaction, we will get this compound. That's what we get. Exactly, because you are eliminating this CH3s remain the same, this remain on the same side. So if you just consider this is an E isomer. Why it is an E? You have the priority between these two is this carbon, this one, this group. A priority between this is a 3 carbon, so it would be up there. So the two high priorities are opposite side, so they are a product. Okay, let me go to the RR now, gives us E. Let me draw the Newman projection for the second one, for B compound. For B compound, if I draw the Newman projection, if I have this, still this is at the back, chlorine is still here from the front, carbon, and hydrogen is still there, and CH3 still would be down here, and hydrogen is here, and another CH3 is here. So this is a Newman projection. So now if you just look at this chlorine and you don't find hydrogen here, so what you have to do, what you're going to do would be to rotate the back so that they would align, either rotate the chlorine back to up, or bring it here, or rotate the hydrogen to come to like this here, anti-periplanar. So I will rotate this. Rotation, the rotation would be, because it's not aligned up now. You need a hydrogen and the halide, like that. So I would just rotate this by 180 degrees rotation. So I would say rotate the back by 180 degrees, so it's clockwise. Rotate clockwise by 120 degrees would give me this Newman projection. After rotation, it would look like, after rotation, I would get, still the front is still intact. I didn't touch the front carbon, but rotation of this by 120 degrees would bring it here. H would be here, CH3 would be here, and propyl would be there. So I'm just rotating only the back. So this is a Newman projection. Now I have lined up a hydrogen to be abstracted and chlorine to live together as hydrochloric acid. This is done if you apply base, anti-periplanar is achieved, and then you have E2. Obviously it is an E2 mechanism. Now I would get this two on the same face and this two on the same face. Propyl is here, CH3 is here, and I would get this hydrogen here, and that CH3 is there. So this is a Z isomer, Z or cis. How is that cis? High priority down here, high priority down here, the same face. That is a Z isomer. Okay, let me go again, do the third one, which is C compound, which is SS. The Newman projection for this looks like, let me draw this, keep the front still the same, so that would be chlorine here, hydrogen here, CH3 here, and propyl is like that, hydrogen is here, and CH3 is right here. This is how the Newman projection looks like by looking from this side. Now if you just look at this hydrogen and that chlorine are at 180 degrees. There is no need to rotate this. So what I have is they are lined up at 180 degrees, this and that. So the elimination would keep that this CH3 and this CH3 are on the same, so base in E2 reaction. This is the molecule does it itself. What we are trying to show you is how it happens. So now you have this group and this group are together. That is, two CH3s are on the same face, and that hydrogen and the propyl are on the same side. So this would give me an E isomer, which is trans. Okay. Now let's do the final one, a Newman projection for the final one looks like Newman projection. Newman projection doesn't change the nature of a compound. I have this propyl, chlorine and hydrogen are, hydrogen is here, chlorine is in, and CH3 is down here. That's the front carbon, this carbon right here. Looking that at the back, CH3 would be here, and hydrogen would be here. So that's the Newman projection. Now we need a rotation for this one, because there is no, this chlorine and CH3 are the ones which are facing anti-periplanar. We need something hydrogen to be here. So what I will do is I will do a counterclockwise rotation, not clockwise, counterclockwise, 120 degrees, meaning that rotation of the back like this, counterclockwise. This is counterclockwise 120 degrees. This will be doing that. So it's for just only for the back, keeping the front as it is. So we'll get the front is still always there. We don't touch the front. Now, if I do this, hydrogen would come here, and CH3 would come right top here. Propyl come down here. So now the elimination would be now easier and lined up. It's set up for good elimination. That's anti-periplanar. 180 degrees, 180 degrees, 180 degrees, 180 degrees, anti-periplanar. Now, the product of the elimination is, if we just look at here, CH3 would be in the top. Let's say just H would be here, CH3 is here, this two, and then I will have this CH3 and propyl, this CH3 right there, and propyl. Remember, in all of this, the base you are always generating HCl is the one which is leaving. HCl has left. HCl is the byproduct. So it's just hydrogen and chlorine they are being taken away by the base. Okay, so this product actually is a Z compound. Z, meaning that this is cis. Why it is cis? High priority down here, high priority down there. Both are in the same direction. So we solve everything now. So as a summary, at least for this compound, the RR stereochemistry and its mirror image, the SS mirror images, give an E compound. The RS SR mirror images give Z isomer. So at least I can conclude from this elimination reaction of a mirror image compounds would give the same stereoisomer. That means their mirror images are SSR. So mirror images are RR and SS. So A and C are mirror images. A, C are mirror images, and B and D are mirror images. So mirror images give the same stereoisomer of alkene. So stereoisomers are the E and Z. So you have to come up with a correct elimination product whenever you are asked to give a proper stereoisomer, because this is stereochemically they are pure compounds, so they should give a specific type of stereoisomers. So it looks a little involving, but it's really fun to just do this over and over so that you can be perfect on solving such problems. We'll continue more on this. All right, moving along, I have an interesting question on this board. This is an E2 reaction, and the question asks which one is faster. So there are a pair of compounds. This is a cyclohexane compound. One is a cis, one is a trans, one is a cis, one is a trans, cis, and trans compounds. So in these compounds, you want to see between the cis form and the trans form, which one would react an E2 reaction, which one eliminates faster than the other. So we'll compare the cis and trans of this, the cis and trans, the cis and trans. Here, the point would be to draw the chair form, the more stable chair form first, and see if you have still the concept of anti-periplanar. So the most important concept is anti-periplanar. That means a hydrogen and the leaving group, which is a halide, have to be in a vertical way and also 180 degrees. One of the concepts. Here I have a 1,2 substitution, meaning that the alkyl halide and the T-butyl. T-butyl is a bulky group. And a 1,3 position, a 1,4 position as well. One important fact from cyclohexane chemistry we learn, a T-butyl always have to be in equatorial position in chair form. You cannot put a T-butyl in axial position. That compound cannot live, that cannot be something that could persist longer time. So you need to draw the right chair conformation for each one of them, where the T-butyl group is always in equatorial position. Fact, this is in cyclohexanes. When we dealt in chapter 5, we said that T-butyl group always has to be in equatorial position. So how do I draw the cis form, the cis in equatorial position where the T-butyl is, would be this form. So they are also in 1 and 2 position. So Br, if it is up there, since they are cis, both of them, I have to draw another one, which is a cis is where both are up. So this is the cis, a stable form where the Br is in axial position because it is demanded that they are cis, but the T-butyl group has to be equatorial at 2 position. This is a demand because T-butyl group is a bulky group, it has to be equatorial. So the cis bromo compound is this one. So this is the most stable chair form. When it comes to the elimination reaction, it has an anti-periplanar with this hydrogen. So luckily, this arrangement gives us a very good elimination product where the hydrogen and the Br are vertical and 180 degrees. Let me draw for this one, for the trans. For the trans, if I have a equatorial position, T-butyl, because it's demanded that the T-butyl has to be equatorial, and the trans would demand the Br to be also equatorial Br, like this. Hence, if you just look at this hydrogen and that Br, they are not anti-periplanar. So this doesn't lead to a good elimination reaction, because you cannot have anti-periplanar between this hydrogen and the Br. Even this hydrogen here, the Br is not in 180 degrees to this. So this doesn't have a good anti-periplanar, but this has anti-periplanar. Hence, this one would react faster. So in the cis form, it is more reactive for E2 elimination than the trans form. So the faster would be this reaction, because it allows you to do the anti-periplanar elimination. And the product for the elimination looks like this would go in, that goes out. So here you have a T-butyl group and a double bond here. So that would be elimination. So base, E2, so that's what you get. So a double bond here, and the T-butyl group would be right there. Okay, let's continue. So in the 1,2 case, the cis is a faster reacting substrate. Let's go to for 1,3 cis, 1,3. So it's 1,3 position. The chair form of 1,3 cis would be, as I said, the T-butyl group has to be equatorial. The 3 position is here, equatorial, and cis. Since they are cis, the Br also should be down. So this also doesn't have anti-periplanar hydrogen. For example, if you take this hydrogen or this hydrogen, they are not anti-periplanar with the bromine. The bromine is down facing. So this will not have anti-periplanar. Let's see the trans one. The trans one, the chair form would look like the T-butyl is necessarily has to be equatorial. You don't have any option for that. Then, since they are trans, the bromine has to be up, because this is up, that's down, that's a trans arrangement. Hence, this one would have a hydrogen that is anti-periplanar. If you just have a plane, this is here, 180 degrees, that could do the elimination much easier. So this is fast. So between the cis 1,3 and the trans 1,3, the trans 1,3 does the E2 elimination faster. But for the 1,2 case, the cis does faster. Okay, let me continue on the 1,4 case. In the 1,4 case, the chair conformation of the 1,4 looks like, and the T-butyl to be equatorial, and they are cis. Since they are cis, it should be Br should be up on top of the plane of the board. Both has to be in a cis form, or both down or both up. So in this case, this is a cis form. Okay, so now if we have this, we have anti-periplanar hydrogen, exactly like what we had in the 1,3 case. So this elimination can go very faster. Anti-periplanar, 180 degrees. So the anti-periplanar is what we look at. But if you just look at the trans, if you just see the trans, the chair form looks like this. The T-butyl group is still up in the equatorial position. You don't have any choice except to put it in equatorial. Hence, they are trans, the Br would be down. This is up on the surface of the chair. Br is down. That is a trans drawing. So you don't have a hydrogen that is 180 degrees straight up for the elimination. So the elimination is much faster for this one. So as a review, if you have a substrate with T-butyl, remember this is a specific case of tertiary butyl locking the conformation in equatorial position. In the 1,2 case, the cis reacts for E2 reaction faster. In a 1,3 condition, 1,3 isomer, the trans reacts faster. In the 1,4, the cis reacts faster. This is in a special case where you have a T-butyl as a substituent. In other cases, smaller than T-butyl, you have to make sure that you have to see both conformations, the total axial, total equatorial, because they can flip between the two. This T-butyl actually locks the conformation in one equilibrium, meaning that the T-butyl has to be always equatorial because it's a bulky group. It can never be in axial position. So this question has several concepts that we dealt with this in previous chapters, but now we're bringing them and we are applying it for this problem. So I really encourage you to see why we have different products for different stereochemistry. Okay, we'll continue more on this. Okay, this will be our final question to solve in the elimination reaction. This is just as an addition when you have a stronger base and as well as two possibilities, two halides that can be eliminated, you would form an alkyne. Not just one double bond, it would be a triple bond. So that's why I call it double elimination. So here you have a dichloro. This is geminal. We call it geminal because when the chlorine or any substituent is on the same carbon, it's called geminal. When they are like this, when they are in two carbons, they are in 1,2 position, or we call them vicinal. Either you should have a vicinal halide or a geminal halide, and you have to have a base which is two equivalents. For each 1 mole, if you have two equivalents, there is a possibility to do double elimination. So this is an example of a double elimination. So you have hydrogen here, and you have two chlorines on this carbon. So the first elimination, the first one equivalent, gives you this product. Right? So one HCl is eliminated, a double bond forms, this leaves, and you have another hydrogen, and you have a very strong base which is two equivalent. You used one equivalent first to form that bond, double bond, and this other base would come and take the second equivalent, takes that, double bond forms here, this leaves. So what you form is a triple bond. This would give you carbon-carbon triple bond with hydrogen, of course, because there is one hydrogen here. So that is an alkyne. So remember now, this is a study of also a functional group. Triple bond is an alkyne functional group. It's an electron-rich, very strong bond. That's a triple bond. So far in our elimination, we are just doing a mono elimination. Now, since we have two equivalents of the base, as well as two halides, either vicinal like this, or geminal like this, we can eliminate twice. So for this one, I will just give you the product. This would be CH3, CH2, CCH3, and you are eliminating twice because you have one hydrogen and one bromine can be eliminated like that, and one hydrogen from this and one bromine. So these two bromines are to be eliminated, and one hydrogen from here and one hydrogen from there. So the product looks like CH, right? No CH, it's already eliminated. You have CH. So this is the product alkyne group. So there is a triple bond right here. So the triple bond is formed between these two carbons because of you have two hydrogens on a beta position, two bromines on the alpha position. Here you have a chloride that can leave, and a hydrogen. So the first one, for example, if it leaves this way, this hydrogen leaves, this one leaves, it gives a double bond, then this hydrogen would leave and that would leave. So the product looks like so it is a straight line. Triple bond sp hybridization gives you a straight line, 180 degrees. So it looks like this. So that's what you get when you lose those. And in the final question, you have both of them in the same. So I would get a product which looks like C, triple bond C, this. So basically, this alkyne is introduced just as a supplementary, because mostly we dealt with alkene with one equivalent of elimination, but this is also a possibility. A double elimination would give you an alkyne compound. With this, we are concluding the elimination chapter with problems. We have solved about 4 videos worth of problem solving, and lecture 23, 24, 25 were also the lecture part of the elimination. So you have enough material to be perfect in the elimination organic reactions. Next, in the following chapters, that is the lecture part, starting from lecture 25, 26, 27, it could be, we will be dealing with alcohols, ethers, epoxides. These are 3 interrelated functional groups. So it would be the 9th chapter, but in the lectures, it would include on alcohols, ethers, and epoxides. These are new functional groups that we're going to be studying. So far, we have been studying alkenes for a long time in the elimination reaction. So I encourage you to follow up with the next lecture on alcohols, ethers, and epoxide, which I will be posting soon. Thank you.